The formula for the grade 11 exponential functions looks almost exactly like the one for grade 10. So you might remember this one. And all we're going to do to it now is add on a p. So you'll know from the parabola and from the hyperbolic function that all that does is shift things to the left and to the right. So let's label the formula. This one shifts things up for positive values of q, and it shifts things down for negative values of q. So it's exactly the same as the other two graphs. This one shifts things left and right. But of course it's going to be counterintuitive. So we're going to shift to the left for a positive, and we're going to shift to the right for a negative. For the A and B values, which are slightly more vague, this is going to tell us the position, and the B value is going to tell us the shape. For the shape of the function, you're either going to get an increasing one or a decreasing one, and the B value will tell you that. So you've got two options. B is bigger than 1, and then you've got a graph that increases. Or B is a fraction. If B is a fraction, then you're going to have a graph that is decreasing. It's exactly like that one, excepting it's been reflected on the y-axis. What B can't be, just a reminder, B cannot be 0 and B cannot be 1. Otherwise, it's not an exponential function and doesn't exist. For the position, we're going to see some reflections here as well. So the A value, if it is positive, you're going to have graphs that point upwards. So that is when A is positive. When A is negative, you're going to have them reflected on the x-axis. So it is exactly like that one, excepting it's down there, and it's exactly like that one, excepting it's down there. To draw the exponential graph, we're going to go through the usual motions. So we're going to get the asymptote, and it's a horizontal asymptote only. We're going to write it down straight from the formula, and then we're going to draw it. Then we're going to get the intercepts, the x-intercept and the y-intercept. If this graph is really high above the x-axis, so if it's there somewhere, then it's not going to have an x-intercept, so where these exist, but mostly they will. And then we're going to plot some extra points so that we have the right shape. I'm going to draw the graph f of x equals 2, that's the A value, then the B value is also 2, to the x minus 1, so we've got a shift towards the right because it's negative, and then minus 4, so we've got a shift down because that one is negative. Right, the asymptote's really easy. The asymptote is just the line y equals q. So, number 1, our asymptote is the line y equals negative 4. With the intercepts, let's start with the y-intercept. So we're going to let x equal 0. I'm going to swap that out for a y. So I'm going to say y equals 2 times 2 to the 0 minus 1 minus 4. When I plug that into the calculator, which is all I need to do at this point, I'm going to get out negative 3. Please make sure that you write down the point, because the point is where x is 0 and y is negative 3. For the x-intercept, and there's only going to be one of these as well, I'm going to let y equal 0. So I'm going to have 0 equals 2 times 2 to the x minus 1, and then I'm minusing 4. Here I'm essentially solving an exponential equation. So I'm going to move that 4 across, and then I see I've got 2 times 2 to the x minus 1. Now these are the same bases. That has a power of 1. I could just add the exponents here, but it won't always be like that. It could be a 3. So a better formula in your head to have for solving these would be to divide by the a value. So I'm going to divide both sides by 2. 4 divided by 2 gives me 2, and then this one is just having that bit on the right left over. So if 2 to the 1 equals 2 to the x minus 1, then 1 equals x minus 1. Solving for x there and moving that negative 1 to the left to become a positive 1, I have 2 equals x. Please write down the point. So this is the point where x is 2 and y is 0. We need extra points to give the shape of the exponential function, because otherwise we're going to end up with something, just the 2 dots in the asymptote. It's quite difficult to estimate the shape, and in exams they always ask you for more points anyway. So your best bet here is we're going to sub in a negative and a positive. I'm going to start with negative 1 and 1. And if that doesn't help me draw the graph, then I'm going to try negative 2 and so on, just so that I can be sure I've got the right shape. Right, so subbing in negative 1, I'm going to get out the y value. So I'm going to say y equals 2 times 2 to the negative 1 minus 1, minusing 4. Plug straight into calculator, and I'm going to get out 7 over 2. Now, why I'm going to write this as negative 3.5 is because it's much easier to plot 3.5 than it is 7 over 2, because my mind is not going to know exactly what that is, but anyone can do halfway between negative 3 and negative 4. This point is the point where x is negative 1 and y is negative 3.5. Write down the point so that you're really clear about what you're going to plot later. Then we're going to sub in 1. I'm going to say y equals 2 times 2 to the 1 minus 1, and then subtracting 4 in the end. When I plug that into the calculator, I get out negative 2. That is then the point where x is 1 and y is negative 2. Now I'll be able to draw the graph with enough shape. The first thing to plot is the asymptote. So I've got it at y is negative 4, so negative 1, 2, 3, 4. I'm going to draw the horizontal dotted line across there. I've got to draw the asymptote first because it dictates where everything else goes. And then I can self-correct if I find that I've made some errors. The next thing to intercepts, so I'm going to plot the point 0 and negative 3. So that is down here. And that's the point negative 3. I'm going to put the points on as I go, or I can do it at the end. And then I'm going to plot the point 2 and 0. So 2 and 0 is over there. And you can see that while I can kind of gauge the shape, because I know what an exponential graph looks like, I don't really know. So I'm going to need to plot some extra points so that I've got the right shape. And I've got them. I've got negative 1 and negative 3.5. So there's negative 3. I know that the asymptote is on y equals negative 4. So negative 3.5 is somewhere between those two. So it's negative 1 there, and negative 3.5 will be about there. And then I'm going to plot the other point, 1 and negative 2. 1 and negative 2 is over there. And you can see that that really helps to give a good shape. Connecting those dots then, I must make sure I do not touch that asymptote because it is something that the graph never goes through. And I have the graph completed. When finding the equation for an exponential function, we've got to remember how it differs from the other ones for the formulas for parabola, hyperbola, straight line. You have y equals ab to the x plus p plus q. So you've actually got 1, 2, 3, 4 things that you have to find, which means they've got to give you more information than what they give you for a different function. So what you'll find is they often give you a partial equation where there's some kind of detail. Often they leave the a out and they just give you b, and they imply that a is 1 or negative 1. So that'll help. And normally you're getting a point, you're getting an x and a y value, so you can sub that into the equation, and often they actually give you the asymptote. So when they give you the asymptote, you're just going to sub into your Q value. You're going to sub a point into X and Y, and if you can see the intercepts, you can see where things have been shifted. You can plug an intercept in as well as the point 0 and the number, or the other way around. And you can solve for A or B, which are usually the ones you end up solving for. The domain and range are relatively straightforward concepts for the exponential function. You can see here that with two graphs that have different asymptotes, one is increasing, one is decreasing, that they both go infinitely left and infinitely right. So that means that the domain is going to be x as an element of real numbers, or x can be anything from negative to positive infinity for all exponential functions. The range is going to be limited by the asymptote. So you can see that this one goes from the asymptote, not including it, all the way up to positive infinity, and this one goes from the asymptote, not including the asymptote, all the way down to negative infinity. So we're going to say that y goes from the asymptote up or the asymptote down. So let's say that this asymptote is the line y equals -4. So this one's range is going to be from -4 all the way up to positive infinity. So that means y is anything greater than -4. In this case, y is anything less than -1. For the increasing and decreasing values of x in the graph, you're going to go back to the ruler test. So here you can see that this graph only increases. And for this one, you can see that this graph only decreases as I move the ruler from left to right. That means that these ones will either increase for all values of x or decrease for all values of x. So for a graph that is increasing, it's going to be for all values of x. So you would say for x is an element of real numbers, or you could write the sentence out for all values of x, or you're going to have it decreases for x is an element of real numbers or all values of x. With transformations, either you get given the transformation and you have to put out a new formula, or you get given a new formula and you've got to explain the transformation. So we get our shifts up and down. So our up is when the Q value increases, and then obviously down is when the Q decreases. So you are subtracting something from the Q value or adding it. So I'm going to show you what that looks like in graph notation. So if, for example, we have f of x equals 2 to the x plus 3, and then we are going to shift it down by 5, then your notation will look like the whole graph down by 5. So you're going to take the whole graph, the f of x as it is, 2 to the x plus 3, and then you're going to subtract 5 on the end. Your new graph then will look like 2 to the x, and plus 3 minus 5 gives me -2. That's going to be the formula for f of x that's been shifted down by 5 units. If you're shifting left or right, it's going to be slightly different. Remember that a shift left is going to be when you are adding onto the p-value. So the p will increase if you shift to the left, and if you shift to the right, you're going to subtract from the p-value. The way that the function notation will look for this is that where you see an x in the original graph, you're going to see a change inside those brackets. So let's say I take the same graph and I shift it 4 units to the right. So now instead of f of x, I'm going to have f of x shifting to the right. I'm subtracting from the p-value, so I'm going to subtract 4. So now it's f of x minus 4. So every time I saw an x in the original equation, I'm going to put an x minus 4. So now I've got 2 to the, not x, but x minus 4. And then I can add my 3 on at the end like it was. So I haven't done anything extra here. There's nothing to calculate. That is the new formula for the graph that is shifted right by 4 units. We're going to reflect graphs in one of the two axes. So if we look at a graph, say y equals 2 to the x, and it goes up like that, cuts at 1. If we reflect that in the x-axis, then the new graph is going to be the mirror image of that one, but in the x-axis. So you treat that like the mirror line, and it goes down like that. So you can actually physically see that what's happened is all the x values are staying the same, but where the y value here is 1, it would be exactly the same number but the different sign in the bottom. So what happens is if you reflect in the x-axis, the y's become negative. And what that looks like in functional notation is the following. Let's say we've got a graph of f of x. We'll take 2 to the x plus 3 again. So that would be that graph, but shifted up. And we're going to reflect that in the x-axis. The way that this will change the notation is f of x is y, and y becomes negative. So we will write a reflection in the x-axis as the negative f of x. So that means that it's negative this whole thing. So negative f of x gives me negative 2 to the x plus 3. Multiplying in that negative, I then get negative 2 to the x minus 3, and that is the new equation of the graph that has been reflected in the x-axis. Now, if we reflect in the y-axis, you'll see from my original graph over there, if I reflect in the y-axis, it means that I'm going to have this as my line of symmetry. So that means that part will go there, and this part will go down there. So it's going to be the graph where b then becomes a fraction, which makes sense, because what you're doing is you're taking the x value, which is in the exponent, and it becomes negative. A negative exponent can be rewritten as a fraction. When we reflect in the y-axis, the x becomes negative. So where we see an x in the original equation and in the notation, we now write a negative x. So it was f of x, it's now going to be f of negative x. That means where we see an x, we write a negative. So it's going to be 2 to the negative x, and then we're adding 3 onto the end. This will give us something that could be written as a fraction, because we're going to get that green graph over there. So I told you earlier that that means b is a fraction, but look, here it is. To write that with x as a positive, I can write it as 1 over 2 to the x, which is the same as saying a half to the x plus 3. So this graph has now changed its b value essentially when I work out the equation to keep the x positive. This is then the new equation of the graph that has been reflected in the y-axis.